also explained in the calculus classes as well, when you have to give the application of the derivatives as well. So if you have already know or have some idea, that would be the addition for this topic. However, this is basically related to a topic of numerical analysis, that is in which we try to find the root of the equation by approximation and making our iteration or our solution better as we move on. So, but question is, if there is a bisection method, and we all know that that method is definitely going to work, as I claimed in the last lecture. So why do we have to know, or why do we have to learn another method? That's the main point. So in bisection method, as I already claimed in the last lecture 6a as well, that it is a very good method, but it's slow, as it depends on the initial choice of the interval. If we choose a and b quite far, then it take longer time to reach to the desired root. To in order to avoid this situation, because in the practical application we need fast convergence means that I want to reach to the root fast as compared to the other method. So in order to do that, we need some other scheme. So one of the method that is we are going to start is called Newton Raphson, and that method has a different approach to find the root of the equation, but that method is much faster as well as compared to the other methods. But there is some condition. So let's see what those conditions were as well. But let's first try to understand how this method works. So same requirement that we have for the bisection. I'm not going to explain again. Consider and consider a non-linear equation. Okay, this could be a transcendental or it could be a polynomial equation as well. So and our requirement is that we want to find the root of the equation. That is, if let x r is the root. Okay, and if xr is a root, then mathematically this means that f of xr is equal to 0. Okay, we have to discuss this method Newton Raphson for one value as well, but we already learned in the bisection method that the same process could be repeated to find the root of the other method. So let's move ahead. So what this line is saying, there exists some nonlinear equation, let's call it y equal to f of x, and I want to find its root, and I have assumed that there exists one root xr, and such that if f of xr is placed in that equation, we will get exactly equal to 0. That is, it will map the function to 0 at xr value. But this is the ideal situation when we can find exact root, but in our approach we already know we have to do it uh, approximately. So let's see how Newton Raphson tries to find this xr. So same thing that I have done many times earlier as well. So let's assume there is one function and I'm only plotting in a first and last quadrant, because other quadrants can extend the concept, but it will not necessary. In fact, I should not plot here. Uh, I should do it in a center. So because I need to make some changes and corrections as well. So that would be much helpful. So this is our uh, axis. Okay, and this is our something like we can say y-axis, and then this is the x-axis, and this is x-axis, this is y-axis, origin, and similarly there is some, I think I need to rub it as well. Okay, no problem. Okay, so in this case then we have a y-axis there, and with this we will get the y-axis representation. It is just a representation for this purpose. Okay, so how Newton Raphson works. Okay, so let's say I plot that function somewhere, and I told you in the last lecture as well, usually I will plot something like this many times. Okay, so I plot that function, and just to make sure that it has one root, I have graphically shown that the root exists somewhere there. So this is the xr. If I can locate that value, my problem is solved. But we have learned that to find this value is not so easy. So not so easy. So how the Newton Raphson method works, it is very simple concept. To start that method, you need to find only one value. So let's say this is the target value that we want to search, but let's say I selected one point here, or I can select here as well, but I have to start from somewhere. So let's say I selected randomly one point x naught. Okay, but I said it is randomly, but it has one condition is that the x naught first of all must belongs to the domain of this function, whatever the function it is. Yeah, that is all the characteristics of the domain must hold on x naught. And the other thing is that f dash of x naught, that is the derivative of this function, must exist at x naught. Okay, and I will let me clarify it further, that this means that it must exist means it must have a some finite value that we need. Okay, so what basically it, because I have only pointed out one values, that's why I'm saying to you let's x naught it must exist. But in general, when you have to apply Newton Raphson method, then all the values that you want to evaluate the function, you have to make sure that its first order derivative also exists on these values. Okay, in simple words, it must not be infinite. That's the easiest way. It could be negative, positive, a small value, a large value, but it must has to be exist, or it should not be a infinite. Okay, so this is the x naught that we have, and I randomly selected. So I know that if I want to find the point on this function based on this x naught, I can do it easily. And the point that I have is this, have this following coordinate x naught, comma. If I put this point here in the equation, I will get f of x naught, and that f of x naught is basically the height of this function. Okay, this is the height of this function. Okay, so I got the point. Simple, in simple words, I just have a point. Now, how the Newton-Raphson method works and what was its strategy? So, what in Newton-Raphson we do? We draw a tangent to that curve. Okay, what does this mean? That what do you mean by that tangent to you have to draw? Is this situation like I have to draw a tangent? So let's choose some other color. I'm selecting a blue color or something because I have to draw tangent many times. So I'm drawing the tangent first time on the first point that I have randomly selected, provided that the derivative exists at that point. So if I draw a tangent there, so tangent we know is a line that touches the graph function at only one point, not intersect, touch the graph. So let's say a tangent, which is represented here with blue or a black color, whichever is that. So I draw it like that. Okay, it intersects somewhere. So it is intersecting somewhere the x-axis. So in this case, it is intersecting this tangent line. So let's call this tangent line T1. Okay, I think using the white color for writing is much better. So let's switch back to that thing. So tangent is this black line or blue line with the T1, and it is the tangent, then it must intersect somewhere the x-axis, as it is not parallel to the x-axis, because we already ensured that the derivative is not it must intersect somewhere. That's what we want. In fact we have not ensured yet, but we have to make sure that intersect must it may intersect very far from it, or further far, but it must intersect. Let's say it is intersecting there because the hypothetical graph, so this is intersecting there. So the point at which the tangent 1, which is obtained based on the point x naught, that is the first point, initial point or initial guess point, we have obtained a tangent, we plot the tangent, and tangent is a line which is intersecting at x at some point. The point where the tangent 1 is intersecting, I will call it x1, just for a sequence. What is the sequence? Using x naught, I draw a tangent t1, and t1 intersects somewhere on the x-axis and I call that point x1. That is, in simple words, I got x1 from x0 somehow with this logic. This is the logic of the Newton Raphson. So this is the tangent that intersect. Obviously, to the line it can continue, but intersection is enough for us. Now, in the latter stage or in the latter part, so this is one way. Now, question is, so how we have find XR? How to find the XR? So what Newton Raphson method do, that using x naught we have computed x1, okay, which is the x-intercept of the tangent drawn on x naught. We do not need such explanation, but this is how we have got it. Okay, so question is, can x1 represents root? Question है, just thought I that is basically the thought at which the Newton Raphson method relies. So okay, this is the tangent that we have got here, but we don't know whether this tangent, this point or x1 is the root of the equation or not. Obviously it is not the root, it is quite far from it. I can see that the error between the approximation and the value is quite far. Although this is not the root, it is the intercept of the tangent, but what Newton Raphson do, it tries to approximate the root by the intercept of the tangent, but as we can clearly see, it is a quite far. But question is it possible that this could be reflected, root could be reflected by the intercept of the tangent? Then your answer is yes, it is possible. If I select x naught, not here, in fact very close to that root by luck, then the if I draw a tangent somewhere there, then tangent is very tangent will be passing from there and it will be very close to the root by luck. It is possible. So this means that although by the given diagram it is not appearing to be the root, but logic of this idea can leads to the root as well. It is just like the bisection. In bisection, when I divide the interval, we not necessarily always get the root, but logic suggests that if we continue to do so, we may reach to the root as well, or there is a chance that we can reach to the root in the first attempt as well. Because if I select A and B such that the root is the midpoint of it, then I can get the result in a first time. Similarly, if I look carefully, we can see that this is not the root x1, because x1 is not equal to xr. But what Newton Raphson tries to do, Newton Raphson tries to approximate that intercept by the root. Says that okay, this could be treated as a root, okay, but obviously we are not going to accept. So what we have to do, we have to move to the option of iteration. We have to move to the iteration, and the iteration is that if we repeat the same process. What is the process? Select a point, draw a tangent, tangent must intercept, and whenever or wherever it intersect, let's use this point as again the starting guess. So I have x naught. From x naught I got the x1 based on this exercise geometrically, and now I want to do the same thing on x1. So this is the x1. Obviously function, I don't know, function may continue somewhere there or something like that. So if this is the x1, let's say I selected x1 somewhere there. This is the point. So the point has a coordinate x1 comma f of x1, because this is the point. So if this is a point, then I can put that point as well, so I can get this height. So this point is known to me. So what I can do, I can try to draw a tangent on this point. Okay, obviously I have selected the graph such that it does not seem. So if I draw another tangent on this point somewhere going this one, so this could be a tangent number 2, t2, which is obtained based on the point x1. So this tangent must also going to intersect somewhere. So let's say if using x naught I got x1, which is the intercept of the tangent t1, and now using x1 I got some other point as an intercept, so I call it x2. Okay, so now we can see that obviously it is just a rough diagram, but we can see that this distance is much higher as compared to this distance. So this means that we are reaching to certain extent close to the root. So if I do the further thing ahead, Same process if I repeat again, so I may get a tangent which is somewhere there, and this process will continue. So ultimately what we are doing, obviously graph is very parallel. This is not the ideal condition, but I deliberately did that because I want to highlight one issue, because Newton Raphson is relying on assumption that a tangent must intersect the x-axis. In other words, tangent must has an intercept. So if by mistake tangent becomes parallel to the x-axis like this one, parallel to the x-axis, maybe here if I draw a tangent, then we cannot find the intersect. So in this case, the method fails. This is the drawback of the Newton-Raphson method. When the tangent is parallel to the x-axis, it never intersects the x-axis, because we know that parallel lines never intersects. So when it does not intersect, we cannot find the root. In fact, the root exists. For example, if I have a tangent somewhere there, then the tangent is going parallel to the root. In fact, root exists, but we cannot find. That is the drawback of the Newton-Raphson method. Okay. So what Newton-Raphson do? Nothing. Just take the point, draw a tangent, and intercept of the tangent would be claimed as a root. If you think that that value is good enough, accurate, then take it as a root. If not, then repeat this process again. Draw a tangent at that point and find another intercept. And if you think that the second intercept is good enough, take it as a root. If not, then repeat this iteration. Then drawing the tangent iteration will continue unless until you will reach ultimately very close to the root. For example, I'm just jumping. Let's say at certain point you reach there and you draw a tangent. So tangent would be somewhere there. Okay, so you select one point again, and then you reach to that point. Okay, and then you draw another tangent which just seems to be very close to it, and then if you find another point you can continue. So if you draw a tangent there, that would be a much closer to the root. So as soon as the iteration starts making, if we just have to make sure that it intercept the x-axis, and how we can do that I will explain to you. So this process will continue and you will ultimately reach to the root. So we sometimes call it line search method as well, because it is drawing a line and trying to find the root where the line is basically a tangent. So this is how this Newton-Raphson work graphically. Obviously, we will not do the graph like drawing the graph and then drawing a tangent with scale and pencil. No, this is not we are going to do. However, if someone wants to do, can represent the Newton-Raphson like that. But we have to do in a algebraic way. This is the geometrical explanation, but we have to do some algebraic way. Keep in mind there are two assumptions so far. Number one, in fact, I have explained only one assumption, but there are two assumptions that on all the points that is the intercepts are our derivative, first order derivative must be defined. At any point, if the derivative is not defined, method fails to converge. Okay, this is the first thing. The second thing is that which I have just highlighted, the tangent must not be parallel to the x-axis. But question may arises when this will happen. Like how do we know that the tangent is not parallel? Okay, so to that let's have another graph just for understanding. For example, if the this is the graph, okay, and you are repeating some process, suddenly at any iteration you find a point here. Let's say some intercept is passing through it, so you said okay, use this as an intercept, so you find a point on it and then you decided to draw a tangent on it. So as soon as you draw a tangent on this line like this one, okay, okay, so as soon as you draw the tangent on this line, so according to Newton-Raphson, it has to intersect. So it's not intersect, it's going parallel all the way. So method fails. However, we can see that root exists somewhere there. So we have to avoid this situation. How we can avoid? Since we already all know that this is only happen when we draw a tangent at the critical point. You remember the critical point from the calculus? This is only happen when we have a tangent parallel to the x-axis. You remember critical points when we call it maxima minima points. We have a condition, we took out first derivative and equated to zero because we want to find the point where first derivative is zero. So what does this mean? When, and we know that this is only happen when slope is zero. So at this point slope is zero, that is derivative of that function is zero. Okay, so in this case, when this slope is 0, then if you draw a tangent to it, it will be a parallel to the x-axis and never intersect. However, the root exists. So this is the drawback of the method, not the root. Root exists, but you cannot find it if tangent becomes 0. So when you are predicting the point based on the intercept of the uh, intercept based on the intercept of the point, like it is the just intercept, so you have no control. Maybe this x1 will be the maximum minimum of this function, because it is not in your control. It is total random process. You selected x0 and you draw a tangent, and the intercept of that point may lead to the maximum. Maybe the function is returning from it backward. This is the minimum value. So in that case, tangent will be the parallel to the x-axis, so your method fails. So keep in mind that whenever whenever during iteration f dash of x, I'm just not referring any value x1 x2, I'm just saying at any point if f dash of x goes to 0, that is your derivative becomes 0, then Newton Raphson failed to converge. Converge means that if I got x1 which is quite far, then I got x2 which is relatively close, then I may get x3 which is further close, and if I repeat this process continuously, I will ultimately reach close to the B point. So this is called convergence. You are converging towards the root based on your stopping criteria, which I already explained to you. So Newton-Raphson converge to fail. This, however, this does not mean that root does not exist. Okay, इसका ये मतलब ये नहीं है कि this means that the root does not exist, that you have to make sure root may exist or may not exist, but if the derivative goes to 0 at any iteration that you have started at any point, then this means that the you cannot draw the tangent that is intersecting the x-axis. This means that this is the drawback of your Newton-Raphson method. Okay, but I already told you this is the geometrical explanation. We don't do like that, drawing and making or trying to find a root. Also we can do that, but this is not a best way. So there must be some algebraic formula that we can apply to find the approximations, and then we will continue unless until we match our stopping criteria. So what would be the algebraic way to express the Newton Raphson method? Is quite simple, which is basically based on what we have done here. Okay, so this how we will do that. Let me explain it again in a proper way with the diagram. So it is a continuation of the Newton Raphson. I'm not doing anything new. So for example, I'm here and the Newton Raphson method needs to be implemented. Okay, so I am here. This is the axis. This is the y-axis. Similarly, this is the origin. It could be explained on the second and third quadrant, but I prefer to explain the method on this side only. This is the x-axis. So now what I do, I have some nonlinear functions. Let's say something like that. This is the nonlinear function y equal to f of x, and I am interested to find the root, and I already assume that its root exists xr, but I don't know. So let's say I have to find a one value. So the value that I have, let's say I'm not going to call it x naught or something, I am calling it x ith. Okay, so if you remember in the previous slide what I did, I selected x naught, and based on x naught I get x1. So I can say that using x naught I have got x1 based on this logic. Similarly, using x1, then I will get x2, and so on. This process continue. So I can say what this is the subscript. So I can generally say that whenever I have xith value, I will get xi plus 1. So if it is not, I get 1. If it is 1, I got 2. If it is 2, I get 3, and so on. So in generally, I can say whenever in any ith iteration, if xi is the initial guess, if xi is the guess, then I will get xi plus 1 as a new approximation of the root. And this process will continue for all i's. Okay, where I represent the iteration value. So iteration number. So for example, I have selected this point, and let's say I call that point ith point. Okay, it could be a first iteration, but then in this case this become x naught. But if it is a more than first iteration, whatever be the iteration, we need one point at which I can draw a tangent. So let's say I draw a tangent there. Okay, this is what we have learned. So we can see that it's just a repetition of what we have done there. Okay, so the coordinate of this point is xi. Let's call it yi, or we can call it f of xi. Okay, now let's draw the tangent. I'm not going to draw the tangent again, because what I am doing here, I am just showing you that repetition in a one instance. Okay, so it will definitely intersect, and according to Newton Raphson, I will claim that intercept as a root. So this is our xi plus 1, because I obtained that point based on the xi. So I got this point. I'm not going to explain again the same process. You know that after that I will draw a tangent there. So I will get xi plus 2, and then I put the tangent again, I will get xi plus 3, and this process will continue. So this is just an indexing. So I got this point. Now according to Newton Raphson, this could be our root. This could be our root, although this does not look like, but I am just showing one instance of the iteration. This is known, this is predicted, this is known, this is we have computed. So let's convert this logic into algebraic. What we have done? So I have one point and the function is given to me. So what I can do, I can compute the equation of this line, which call it tangent. So I'm just not calling it, let's say this is ti tangent. So I can compute the equation of this tangent. How I can do that? We have xi, yi or yf of xi, whatever. Yi is basically is the value of the function at this point, so I can call it like that as well. Okay, so we have xi and f of xi, or in short yi. So this is given to us, and now we need to find the equation of a tangent that passing through this. We need very basic calculus to drive this formula, and it is very simple formula. So to do that, we note that the slope, okay, slope at this point xi f of xi. So what would be the slope at this point xi fi? We know that we, because this is the function, so and it is given to us, that is the function at which we have to find the root. So what I have to do, we just need to draw the tangent or an intercept over this line. Okay, so if I do so, what will I get? If I we have to find this, so we have to draw the tangent. So tangent is there, so at this point the slope of this function and the tangent is same. We know it from the basic calculus, so we can find the f dash at the point xi. So slope is basically equal to f dash at xi. Okay, okay, so now we have a one point, okay, on the line, and the slope of the line as well, because the slope of the line remains constant. However, at this point, whatever the slope of line is, we have a function at the same point as a tangent. So now this is the slope of the line, and this is one point that lies on the line, so we can apply slope point form to get the equation, and we all know the equation will be defined like that for any point that is on this x-axis. So using slope point form, the equation of tangent is given as, okay, the equation of the tangent, I'm not going to explain this basic formula, but equation of the tangent could be defined like that. f of x minus the point at which we are working on it. So we are working on this point. Okay, so f of xi divided by x minus xi, where x could be any point on this line. Okay, x could be anywhere on this line. So whatever be the point x is, we can find the value of the function as well. Okay, so this is the important point that you have to compare, because this is the slope, so I can do that thing. The slope of any along this line is same. So this thing is equal to f dash of xi. Now the student may be confused that says it's a tangent and this is the value of the function. But what we are doing, we are saying that if this tangent is very close to that point, then the approximation can be made there. And how? Let's see that. So this is basically the representation. The slope is like that. However, if x could be any point, then the point which is the intercept, we have one issue. At the intercept, this value must be 0, because x could be any point, then x could be x at x equal to xi plus 1, because x could be any point, so x could be an intercept as well. So if it is an intercept, then the equation of the tangent will be changed, because at this point we are claiming that this point is a root of the equation of this equation. So if it is the root of this equation, then this part must goes to 0, because this is the definition of the root. If you are claiming it to be a root of the equation, then f of x must be 0 at that point. So according to Newton Raphson, if xi is the point that I have used, then xi plus 1 could be a root. So if it is a root, then as xi plus 1 could be a root. Okay, it's not necessary, but this is the assumption, this is the approximation. Then if this, in this case, what we have, if I, because this is the equation of a line and this point intercept lies on the equation, then it must satisfy this line. So this means that if I compute this quantity f of xi plus 1, I have just put xi plus 1 in place of xi. That is the only thing I have done. Xi plus 1 minus xi is equal to f dash of xi. Okay, now if this is the part that has been done there. So as we know, if we have to claim that xi is a root, as xi plus 1 is claimed to be a root, this implies f of xi plus 1 must be equal to what? 0. It has to be 0. Agar if we have claimed that this is xi is the root, then this thing must be equal to 0. So let's see it. So when we put that value under this condition, so this term goes to 0. Whatever is left is 0 minus f of xi divided by xi plus 1 minus xi equal to the derivative of the given function at xi. So if I look carefully, I know this thing. I know this thing because function is given. I can compute its value. I know this thing because xi is selected. So I know about xi. The only thing which is missing is xi plus 1. I don't know that xi plus 1 quantifiable. Although I know that this is the intercept of the tangent. But to have a quantifiable answer, that I can say it like that. The xi plus 1, if I solve for xi, okay, I'm doing directly, but you can try it to solve it. When you solve for xi, you will get the following formula, which is you all aware of very well. Okay, so I get f of xi divided by f dash of xi. F dash is only dividing the denominator. So if you multiply this thing and try to solve for xi plus 1, you will get the following representation like that. Okay, this is the representation for, and this formula is not only for one point xi and xi plus 1. Xi and xi plus 1 represent transitions. Okay, they represent transitions. There could be any point. If it is x naught, then this become x1. If this is x1, this become x2, and so on. So this formula is not for only one instance. they exist for different indices for all I, 0, 1, 2, and so on, unless until you achieve your convergence. Okay, this is the iteration. I0 means first iteration, I1 means second iteration, I3, I2 means third iteration, and so on. So this is how the geometrical representation of this whole process works. Okay, because we claim that the intercept can be regarded as a root here. If you look, I said that in a one instance that x1 could be regarded as a root. So in general, derivation would be like that. So whatever we are getting is just an intercept of the equation, but equation or tangent, but that equation gives the root. We are claiming that Newton-Raphson claimed that this could be the root of this equation. Okay. So this completes the derivation that now how we have to use it. We just need to select one point, any of the point randomly. Then we say let's start the iteration number one. We will index I0, so this become x naught minus f of x naught divided by f dash of x naught. This will give me x1. Then x1 become the input, x1 minus f of x1 divided by f dash of x1. This whole calculation will give me the x2. Then I got I equal to 2. This means that x2 minus f of x2 divided by f dash of x2. This will give me x3, and this process will continue. This is the same algebraic calculation as we are doing by drawing the tangent geometrically. Okay, so this is just an equivalent of the geometry. Now I have pointed out that derivative must not be zero, because we know that in geometrically if derivative is zero, it is only happen at the maxima and the minima. So in this case the tangent will be parallel and method fails to converge. So in this case, does this condition is also reflected by the algebraic formula? Yes, we can see that if that there's the derivative is appearing in the denominator, and if denominator goes to zero anywhere on any value of xi, this means that this method fails to converge, because we know that denominator means infinite if it is goes to zero. So this means that this formula for these indices provided that at any calculation step f of xi must not be equal to 0. Okay, if it is 0 it is possible because not in your control, you just start it. But if it is goes to 0, then you have to restart your iteration. Okay, so this is the drawback of the Newton-Raphson. However, if you manage to avoid this situation by luck, then you will get the fastest convergence. That is, you will reach to your desired accuracy, or based on your stopping criteria that you have defined, faster as compared to the all other methods. So usually in Newton-Raphson we say one word, or in text we can find that Newton-Raphson is faster if converge. Okay, and when what does if converge means this thing, derivative must not goes to zero. Let's say after performing 5 iteration this goes to zero, then you, this does not mean root does not exist. Root exists, but you have to start it again. Okay, so this is the one of the method. As I already pointed out, I will cover the methods first, and then in later I will solve one example or extra tutorial in which I will solve this computation, that how we have to use that formulas in a data wise, and then you will see the comparison. Okay, so this is how the method of Newton-Raphson work or develop. Let's continue further, or we can have a break here, because this is also the around roughly of 40 minutes. So this could be this is our lecture number 6b, in which we have derived the Newton-Raphson method. This is the formula that you only have to remember, but keep in mind, okay, make sure that this is whole divide, only it is dividing there, and then you have to subtract it from the xi. Okay, so this will be the Newton-Raphson formula, that is fastest method to find the root, but provided that you converge and you start by making any guess. There is no need to bound the root. If you do it, it will be a good for you. But if not, then method does not require it. Method will continue to search for the root. Okay. So this is the lecture number 6b.